Sound is a wave that can have all the same wave properties listed in the first chapter. They include reflection, absorption, transmission, refraction, diffraction, interference. These basic properties are like fingerprints that help us identify something as a wave. And here is a very famous print by Katsushika Hokusai, The Great Wave off Kanagawa. Sound waves share the same properties as water waves. The reflection of sound off an object is called an echo. When a sound wave hits a barrier or a boundary, it is reflected back. Sonar, which is sound navigation and ranging, uses the reflection of sound waves to map the seafloor of our oceans. So here we have a device sending sound waves down, hitting the floor of the ocean and coming back. The boat is towing this towing device that emits sound signals. They get reflected off the seafloor back to the device. They are then analyzed to find the distances to the seafloor. Some animals, such as bats, and actually dolphins too, can see how far food is away by judging how fast the sound waves return after reflection. This is called echolocation, very similar to sonar. To measure the speed of sound in a medium, we divide the distance it travels, that's d, by the time it takes for the trip. Again, one of the first equations we learned in physics. The speed of sound varies in different media, just like the speed of light varies in different media. The speed of sound is faster in solids and slowest in gases. That might seem counterintuitive, but it's true. And liquids fall somewhere in the middle. Solids have a greater density of molecules, and by density we're talking about mass per unit volume, than liquids and gases. So the solids molecules are closer to each other. Sound waves are transmitted by molecules striking each other. That was that picture we showed a few slides ago, the little moving picture, where we had the plunger moving back and forth, and all the particles would hit the guy in front of him, who'd move, who would then hit the next particle, who'd hit the next one. Meanwhile, the actual particles are just going up a little bit and coming back. So, since sound waves are transmitted by molecules striking each other, in denser media, the molecules spend less time traveling before hitting the next one, resulting in a higher wave speed. In addition to density affecting the speed of sound in media, so does temperature. Molecules in warmer air move faster than molecules in colder air because they have more energy. Right? Warmer molecules have a greater kinetic energy because they have a higher temperature, so there's just more energy in the warmer molecules than the colder one. More energy, they move faster. And how does that work on the graph here? This is a chart for all the materials at 20 degrees Celsius. These were all at 20 degrees Celsius. But they have the one reading here for cold air at 331 meters per second. Now, cold air is denser than warm air, so by the logic on the previous slide, the sound should move quicker through cold air. But the temperature is more impactful than the density in this case. So warm air, we've got sound moving at 343, cold air 331. Look how fast it moves in iron and steel, 5,000 meters per second.